Hello, this will be lesson 2.3, scientific notation with negative powers of 10. So let's get started. I'll share my screen with you. And here we go. Okay, like I said, this is going to be negative powers of 10 with scientific notation. The last lesson was the positive powers of 10. So we were looking at very, very large numbers. Now we will be looking at very, very small numbers. The standards are still the same. I can write a number in scientific notation and I can write a number in standard notation. We're still working in EE3, but this time we are going to be talking about the very small quantities right there. So we will be doing the same standard EE3 using very small quantities. I'm going to minimize myself and we will begin. Here's my math meme for the day. So you're saying scientific notation shortens numbers? It must be a Jedi mind trick. Okay, here we go. So again, what's the definition of scientific notation? Scientific notation is a method of expressing very large and very small numbers as a product of a number greater than or equal to 1 and less than 10 and a power of 10. Today it's going to be the negative powers of 10. So for example, this number 0.000000003 written in scientific notation is 3 times 0 times 10 to the negative 8. By the way, what is 0.000000003? How would you read that number? You would read that as 3 billionths with a TH at the end. Just a little more math for you. Okay, writing a number in scientific notation. So we're going to write 0.000024 in scientific notation. That is tens, hundreds, thousands, 10,000s, 100,000s, millions. That's 24 millions. So step 1 is to move the decimal point until you make a number between 1 and up to 9.9 or 9.99, just as long as it's less than 10. So it's the same as we did with positive powers of 10, except we're going to go the other direction. So there's our number. There's our decimal point currently. So we're going to move 1, 2, 3, 4, 5. So we're going to stop there because we have the number 2.4 when we move the decimal, and that's a number between 1 and 9.99. So 2.4 is going to be the number we use. Step 2, we're going to count the decimal jumps. We had 1, 2, 3, 4, 5 decimal jumps. 5 jumps, and notice that we're going to the right this time. In step 3, we're going to write our new number times the negative power of 10. That equals how many jumps you made with your decimal point. We made 5 jumps. So the correct answer then would be 2.4 times 10 to the negative 5. Okay, just the opposite direction. Let's try another one. This one is 0.0000829. We want to write this in scientific notation. Go ahead and pause the video. Try it first on your own, then come back and watch me do the correct steps. Okay, step 1, move the decimal point until you make a number between 1 and up to 9.9 or 9.99, as long as it's lower than 10. There's our number and there's our decimal point. So we have to move it to the what direction? Exactly, the right. And how many do we move it? Until we get a number that's between 1 and less than 10. So let's move it. 1, 2, 3, 4, 5, and I'm going to stop there because now I have 8.29, and that number is between 1 under 10. So 8.29 will be the number we use. What's step 2? Count your decimal jumps. We did, right? 1, 2, 3, 4, 5 decimal jumps, and they were to the right. So we know that our exponent is going to be negative. So we're going to write our new number times the negative power of 10. That equals how many jumps you made to the right. 8.29 times 10 to the negative 5. Okay, what's the difference? Very large versus very small numbers in scientific notation. Let's take a look at the comparison. When writing very large numbers in scientific notation, move the decimal point to the left, that direction. Your power of 10 has a positive exponent. The number of jumps that you made, that's your exponent. When writing very small numbers in scientific notation, move the decimal point to the right, that direction. And your power of 10 has a negative exponent. Okay, that's the difference. Okay, you're going to have a chance now to give it a try. So I'll see you back in a moment. Okay, welcome back. Hopefully you did well on negative powers of 10 with scientific notation. Let's continue to talk about standard notation. Just like with our positive powers of 10, you can use the normal way of writing numbers to write it back in standard notation. So, for example, 2.33 times 10 to the negative 6 can be written in standard notation as 0.0000233, a very small number. So let's see how to do that. So we are going to write 1.045 times 10 to the negative 6 in standard notation. So here are our steps. Step 1, we're going to move the decimal point, the number of places shown in the absolute value of the exponent of the power of 10. So since it's negative 6, we're going to move it 6 spaces. That's the absolute value of negative 6. So there's our number, and there's where the decimal point currently is. Now we're going to have to move our decimal point to the left to make our number get smaller. Remember, on the last lesson, we moved our decimal to the right to make our number get bigger. But now we're talking about negative exponents, which makes our number get smaller, because we're really dividing by 10 to the power of 6. So that's really the division of that. Okay, so negative 6 is going to become 6 units to the left. So here we go. There's 1 space, 2, 3, 4, 5, 6 spaces to the left. That's where our decimal is going to move. Okay, and what are we going to do with our empty spaces? Just like we did in the last lesson, you guessed it, we're going to put zeros in those empty spaces. So fill in your empty jumps with zeros. So here I am filling in each spot with a 0. And so we don't have to worry about putting commas in these kind of numbers because they're very small, and we don't put commas in very small numbers. So that is the final answer. By the way, how would you read that number? Let's see, tenths, hundredths, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions. So that's 1,045 billions with a TH. Let's try another one. 9.9 times 10 to the negative 5. We're going to write it in standard notation. Step 1, we're going to move the decimal point, the number of places shown in the absolute value of the exponent of the power of 10. The absolute value of negative 5 is positive 5, so we're going to move our decimal 5 to the, what direction? The left, because we want to move it and make it smaller. There's our decimal point, nice and big so we can see it. There's where we're going to move it. So we're going to move it 5 to the left. So here's the first move. 1, 2, 3, 4, 5 units to the left. And our decimal is now going to be put in that spot. Okay, and now what are we going to do with our zeros? with our empty spaces, I gave it away. We're going to put zeros in place there. So fill in your empty jumps with zeros. One there, 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 and there. And then we are done, and we just rewrite our number, 0.000099. That's tens, hundreds, thousands, 10,000s, 100,000s, millions. That's 99 millions. Okay, now it's your turn to give it a try. I'll see you back in a moment. Welcome back. Hopefully you did well in writing those numbers in standard notation. Let's move on. Let's talk about scientific notation in real life. So we have a single atom of oxygen has a mass of 2.66 times 10 to the negative 23 grams. Holy cow, that's a big number, right? Or a very small number. Which one is it? Very small. What would the mass of 2 atoms of oxygen be? Write your answer in scientific notation. Let's see how to do this problem. So step 1, you're going to write your number in standard form. This is only until we learn a different method in our next lesson. So how would we write 2.66 times 10 to the negative 23 in standard form? Look at that. We would move our decimal from this spot. Let me get a little spotlight here. From this spot here, and we would move it 23 jumps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Look at all those zeros. Notice how there's 22 zeros because we had to do one jump past the 2. Okay. Now what's our next step? We're going to multiply our answer by 2, or we could double that answer and add it, right? We could add all those zeros plus 266 there and add it, or multiply it by 2. So when we do that, we get this number. That is the same number of zeros, I believe. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yes, so how did I do that? Well, I multiplied this whole number by 2. And notice what I get when I do that. 2 times 6 is 12. Carry the 1. 2 times 6 is 12 plus 1 is 13. Carry the 1. 2 times 2 is 4 plus 1 is 5. And then it would begin with 2 times 0 is 0. It's a bad 5, isn't it? And then the next one would be 2 times 0 is 0, which is going to be another 0, etc. And then another 0. So you can see how I got that number. So let's clear that. And then the next step is to write it back in scientific notation. Well, let's do it together. We're here with our decimal. We need to get it way over where? Right, between the 5 and the 3, because 5.32 is between 1 and 9.99. So we have to count how many jumps that is. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Notice how it's also going to be a negative 23. Keep that in mind for our next lesson when we start multiplying with scientific notation. So it's going to be 5.32 times 10 to the negative 23. There it is, 5.32 times 10 to the negative 23. Take a look at another one. Oops, that one didn't have the annotation put in, or the animation. Convert the length 7 centimeters to meters. Compare the numerical values. Here, let me just hide that. Pretend like you didn't see that last step and the answer. There we go. Okay, so we're going to convert the length 7 centimeters to meters. We're going to compare the numerical values when both numbers are written in scientific notation. What do you notice? Okay, step 1, convert centimeters to meters. So when we are writing and converting in metric, I don't know if you remember this or not from maybe 5th grade or 6th grade, you have millimeters, then you have centimeters, and then you have decimeters, and then you have meters. And when you're converting from centimeters to meters, you go 1, 2 jumps. So that means you're going to move your decimal 2 to the left. So we will move that when we convert. Oh, there went my thing. Okay, so converting 7 centimeters to meters becomes 0.07 meters. We're going to divide by 100, which moves the decimal 2 places to the left, which we just showed you. And then we're going to write 7 centimeters and 0.07 meters in scientific notation. So 7 centimeters, believe it or not, you can do this. 7 times 10 to the 0. What do we know about 10 to the 0? What is any number to the 0 power? It's 1, right? So it's really 7 times 1, which makes sense because we want to have 7 as our answer, right? So 7 times, this is really the number 1, and that's okay. And then 0.07 would be 7 times 10 to the negative 2, because we move our decimal 1, 2 spots to the right. And then we compare them, and you can see the answer already there. Both have 7 as the first factor. This has a 7, and this has a 7. And they have different exponents. How much do they differ by? They differ by 2. So 0 here and negative 2 here. So they differ by 2. So that's just something interesting to note. Let's move on. Okay, think about it. What are we thinking about it? Which of the following numbers are written in scientific notation? 0.854 times 10 to the negative 3. Is that written in scientific notation? I hope you said no, because the number needs to be between 1 and 9.99. And 0.854 is lower than 1. Okay? The next one is 3 times 10 to the negative 1. Okay, you may have heard my dog there barking in the background because I'm doing this video from home. So 3 times 10 to the negative 1, is that in scientific notation? You should say yes. Why do you say yes? Because the number is between 3 and 9.999, right? 3 is between that, and 10 to the negative 1 is a legitimate power of 10. The next one, 25.8 times 10 to the negative 2. Is that in scientific notation? No, right? Because the number needs to be between 1 and 9.99, and 25 is way past that. Let's try one more. 6.5 times 10 to the negative 4. Is that in scientific notation? I hope you said yes, because the first number is between 1 and 9.99, and 10 to the negative 4 is a power of 10. Okay, let's think about it some more. Which measurement would be least likely to be written in scientific notation? The thickness of a dog hair. The radius of a period on this slide. So this little period here, the radius of that period. The ounces in a cup of milk, or the mass of a proton. Which ones can we eliminate? Which ones would be helpful to be written in scientific notation? Well, we know that the radius of the period on my presentation there would be very, very, very small. So that would be a good candidate for writing in scientific notation. Also, the thickness of a dog hair would be very, very, very small. So that would also be a candidate for scientific notation. And the last one would also be a good candidate for scientific notation. However, the ounces in a cup of milk is not that small, so that one would not be written in scientific notation. That would be the number 8 ounces, correct? And that would not be something you'd write in scientific notation. Okay, now it's your turn. See you back in a minute. Okay, welcome back. Now we're going to focus on some higher order thinking. When a number is written in scientific notation, how can you tell right away whether or not it is greater than or equal to 1? How can you tell when it's written in scientific notation? Any ideas? I'll give you a hint. It has something to do with the exponents. If the exponent on the 10 is positive, the number is greater than or equal to 1. If the exponent on the 10 is negative, the number is less than 1. That's how you can tell. So if I had 10 to the 5th power, that's a positive number, right? That's 10 times 10 times 10 times 10 times 10. If I had 10 to the negative 5 power, that's the same as 1 over 10 to the 5th power, which is 10 times 10 times 10 times 10 times 10. And then you would divide 1 by that. So that's a very small number. And the next slide, write the following diameters from least to greatest. There's all of our numbers in scientific notation. Now, granted, you could write all of these in standard notation and figure it out from there, but there is an easier way. You can look at the exponents. So 1, if you examine the exponents, the smallest number will be the smallest negative exponent, because that's the number that's going to be divided on the bottom by the biggest number, so to speak. So if we get our second one, the largest number will have the biggest positive exponent, okay? So I want to bring the number line out here. So these are exponents ordered on the number line. You'll see that -3 here is the smallest exponent, whereas +3 over here is the biggest exponent. Remember that numbers go from left to right and get bigger from left to right. Okay, so which number, looking at the exponents here, hopefully that black bar will go away. There it is. Which one of those exponents is farthest to the left on the number line? Did you say 10 to the -3? Then you are correct. That is the smallest number. So we'll bring that up here in first place. 5.85 times 10 to the -3. Okay, which one's going to be the next smallest? Now we're getting a little bit bigger. So looking at these, I would say the -2's would come after that, right? So here's -3, the first one we did. Now we're going to the -2's. However, there's 2 of them, right? So now we have to look to the other number that's multiplied by them, and we have to pick the bigger number that's multiplied by them, because that number is smaller. So the next number then would be 1.5 times 10 to the -2. I mean, we take the smaller number, not the bigger number. Sorry about that, because we want to take the number that's smaller first, because we're going from least to greatest. So 1.5 is smaller than 2.3. Then we would next do the 2.3 times 10 to the -2, because that one also has a -2. This has a bigger first number. And then what would be next? Either 1.2 times 10 to the 2nd, or the bottom one, which is 9.6 times 10 to the -1. I hope you said 9.6 times 10 to the -1. That would be next. And then finally would be 1.2 times 10 to the 2nd power. That's how you order numbers in scientific notation from least to greatest. If all else fails and you get confused, you can always write the numbers in standard notation and then compare them. That will work as well. It's just putting more work upon yourself. Okay, I'll give you a chance to order some numbers in scientific notation. Okay, welcome back. I want to play this song for you, and then we will be near the end of our lesson. Oh, I have to go back. There we go.
Some numbers are really big, some numbers are really small. I wish there was a way to easily express them all. Hey, I found there's an easy way to show extreme scientific play. Scientific notation does it easily. And now I love science more than I ever did before, can't you see?
And math.
Express your number so that it's more than one, but less than 10. Take that number and multiply it by 10 to the proper exponent. 300 in scientific notation is 3 times 10 to the power of 2. 10 to the power of 2 is 100 times 3, that's 300, so there's your proof. Scientific notation uses exponents. Go with the base of 10, so you don't have to write out so many zeros again, and again, and again. Take a number like 0.0023, plug it into 8 times 10 raised to the power of b, where a equals 2.3 and b is -3. You get 2.3 times 10 raised to the power of -3. Express your number so that it's more than one, but less than 10. Take that number and multiply it by 10 to the proper exponent. 0.03 in scientific notation is 3 times 10 to the -2. 10 to the -2 is 0.01 times 3, that's 0.03, so yeah, there's your proof. Express your number so that it's more than one, but less than 10. Take that number and multiply it by 10 to the proper exponent. When you use scientific notation, you become a real hero. It's 5.2, it's not a trick, it's 5.2 times 10 to the power of 0.
All right, there we go. Oh, I want to play it again here. Okay, let's go back. And we'll move on. We're on to our very last ending of our lesson today. So your lesson 2.3 will be on Google Classroom. And I will see you guys back in the next lesson. Have a good day. Bye.